Hi, everyone. Welcome to today's session. Today's session will be discussing unlocking the quantum's potential and looking at Alice and Bob's approach to fault tolerance. And it's a timely moment for all of us to be talking about quantum computing. At Everest Group, we've been tracking this space for a little while now. And as we all know, 2025 marks the International Year of Quantum Science and Technology, a global celebration of the century-long innovation that's happened in this space, answering fundamental questions about how nature works and how we have reached the edge of engineering machines that compute the rules of quantum mechanics. We would like to take this opportunity to, discuss what's happening and what's exciting to look forward to. And we also appreciate the journey that this technology area has been led by legendary physicists, right? Starting from Niels Bohr to Albert Einstein to Erwin Schrödinger, who gave us the wave equation and the thought experiment, the quantum cat. And now it's an engineering reality in Alice and Bob's lab. So that's why we have Juliette with us today. And it's quite a significant milestone in many ways, talking through what Alice and Bob is doing. And and we want to welcome all of you who are joining in live. And we would like to encourage all of you to, drop in the chat box where you're joining from, and if you're working with quantum computing in any form, we'd love to hear and know from you what you think about quantum computing, and is it still inside the box or is it quietly coming out alive? And this is exactly where we would like to introduce our guest today. Joining us is Juliette Pernet, the US General Manager of Alice and Bob. She currently brings both the technical depth and strategic foresight into what it takes to commercialize the next generation of quantum computing as a platform. Juliette will help us unpack what fault tolerance means in practice and how Alice and Bob's roadmap is evolving and where they see the real quantum utility emerging first. So just a quick introduction about Alice and Bob before we bring in Juliette and also introduce our other panelists and analysts from this group. So Alice and Bob is a visionary leader. As we look at different companies in this space, we believe that Alice and Bob's approach to fault-tolerant quantum computing is one among the most exciting in terms of what it could potentially achieve. Their work is a direct response to Feynman's challenge. Instead of scaling noisy prototypes, Alice and Bob is committed to building a fully fault-tolerant universal quantum computers from ground up, which means they're using a unique qubit technology, which is called the cat qubit. Interestingly, that is engineered to fight noise at a physical level, and also mastering error correction to designing a 5-stage roadmap towards scalable, useful quantum systems. So Alice and Bob, according to us, represents a bold and technically focused innovation approach. And this year, we would like to spotlight Alice and Bob. So with that, let's dive into the conversation. Juliette, welcome to the session. We're excited to have you with us.
Yeah, thank you very much for having me. It's a real pleasure, and for organizing this. Really happy to chatting today.
Awesome. So again, welcome to everyone who's joining. I would like to hand over to Kasturi. So Kasturi leads our research within Everest Group for all things related to next generation computing paradigms. And quantum computing is one of those. And we also cover neuromorphic and optical, among others. So we'll just kick things off with a brief overview from Kasturi on what our research track related to FTQC does, and take us from there.
Sure. Thanks, Isaac. Hi, everyone. So what I would like to do is take a few minutes to share the latest research on our fault-tolerant quantum computing. And here's the big idea. So we see FTQC as a non-negotiable foundation for what we think is truly scalable quantum computing. And we also feel that it's not about building fault tolerance towards the end. It's from the ground up. So in our research, what we did is we peeled this apart by starting with the tech landscape. And here's how we looked at it. We have actually looked at it from a stack perspective, which has different layers. The first, we have the error suppression, which acts as a frontline defense, more like having hardware layouts, tunable couplers, pulse shaping, basically which makes the system less noisy to begin with. The next layer we dealt with is the error mitigation, which is more of a software fix. And it's where we try to model the noise and subtract it out. So it helps us to get better results, even if you're working with an imperfect hardware. And then at the core, we had the error correction, and that's where you can encode logical qubits across lots of physical ones. So even if few qubits mess up, the system is going to keep going. We have explored codes like surface codes, LDPC, bosonic codes like cat qubits. And what really matters was the speed, where you need real time decoders that can fix errors as they happen. From there, what we did was we zoomed out to explore the drivers shaping up the space, basically like policy moves, private investments, big shifts which are happening in terms of R&D focus. And then we got into real world applications across pharma, finance, automotive, and defense, places where FTQC is already shaping up in terms of long term planning. What we then did set the layout for value chain, who's doing what across the hardware, control systems, compilers, and services. And then we benchmarked different sorts of techniques that we saw side by side, what's gaining traction, what's being experimental, and where the innovation hotspots were actually lying. And very interestingly, we also came up with certain case studies. One was obviously Alice and Bob, and then we had IBM and Rigotti. Apart from that, what we did was we also analyzed the investment and patent landscape, the funding trends, and we also came up with the market potential for the next 5 to 10 years. And also, in terms of a very strong roadmap, how we see the technology innovations will span up in this FTQC phase in the next 5 to 10 years, and what sort of strategies that stakeholders need to take. So the bottom line, what we found based on all these analysis is FTQC is not an optional thing. So if you want quantum to move from one promise to a product stage, we need systems that are fault tolerant by design and not by correction. And this is where the research laid the foundation for the roadmap and in terms of how we get there. So this is how we dealt with that. And coming in terms of how we saw this, what are our main convictions? We had three of those. The first one being FTQC is the ultimate goal, but not an immediate destination. It means that it is not a future upgrade. It is the goal we must build towards from the start. Our next conviction was hardware efficiency and error correction will determine the winners. And the winners will be those who make quantum hardware more efficient, especially by using very few physical qubits per logical qubit and also advancing error correction methods. So that was a second conviction. And a third main conviction was FTQC race will be won by those who are going to build it from scale, from the start, and achieving economies of scale. So companies that build fault tolerance into their systems from day one, rather than patching it later, will be the best in position to scale this up more reliably and also meet enterprise needs. So, having said that, what we found was Alice and Bob have taken a long term deliberate approach right from the start. They're focused on building fault tolerant quantum systems from the ground up. As I mentioned earlier, this is what one needs to go up when they need to become a winner in this space. And so instead of chasing short-term performance wins, they've been engineering for logical fidelity, robustness, and architectural simplicity. So we think that it is a strategy um, that prioritizes reliability and scalability in a more lasting way, rather than patching things up later. And that's what will enable organizations to win a competitive edge in this space. Having mentioned all these points, so I would like to ask Juliet this question, a very important one. What actually drove them to commit to full scale tolerant, like a fault tolerant system starting from day one, rather than taking a very incremental innovation approach, which most of them are doing? Over to you, Juliet.
Yeah, thank you very much, Kasturi, for this great analysis. So first, I want to highlight that it was our founder's intuition that in order to reach utility and usefulness with quantum computers, you'd need fault tolerance. And if you look at what this intuition is coming from, it's clearly from the fact that to date, this fault-tolerant algorithm are the only ones that have demonstrated value. So nobody was sure that NISC was not going to deliver any value at this time, and there's still like a potential for it. But as times go, we kind of like prove with time that it's going to be harder and harder for NISC to keep on their promise. It could still happen, honestly, that innovation or a new optimization, I don't know, could unlock value through NISC, but it's becoming more unlikely as all the community knows more about it. So that's kind of like what really pushed our founders to really build the company and its technology with fault tolerance in mind. And as they were also researching cats in their own studies, it also resonated with their actual work.
That's very interesting. So you have become like more of a visionary innovator and then an early adopter in this field of fault-tolerant quantum computing.
And we're not the only ones. Like there's other players that adopted the same strategy from day one. Can name like PsiQuantum that hasn't been developing NISC hardware. So we are not alone. It was just a little bit harder, I would say, to convince potentially investor or end users to shift their attention from NISC to FTQC from day one, when there was still a potential for these intermediate algorithm.
Great to hear, Juliette. So I have one more question for you. What we find is one of the things that makes Alison Bob's technology stand out is basically the use of something which we call it as the cat qubit, which also Isaac mentioned earlier, which the name comes from Schrodinger's cat, where something can be in two states at once. And that's what exactly we think how qubits work. So instead of using the usual types of qubits, which uses you are using a special electromagnetic state that are more naturally stable. So what we think makes you stand out, and also in terms of handling certain types of errors, especially the phase flip errors, which is like a common problem in quantum systems. So this can be better handled with this sort of qubit. So what we like to understand is what exactly makes the cat qubit very special, and how is it helping Alison Bob gain a competitive advantage in the FTQC space?
Yeah, maybe just to go back a little bit on what like the requirements for fault tolerance is that when you correct your errors, which are inherent to any type of computing system, you want to correct them in such way that by adding more bits or qubits to your system, you're correcting more errors and not adding them as you're adding potential sources of noises. And the main advantage of Alison Bob's cat qubit technology is that we correct these errors with our technology, not by adding error correction code on it. So we don't correct all of it, though. It's just one dimension, which is the bit flip error rate. And the great advantage of that is that other platform will have to implement error correction codes that have two dimensions to correct for both of these errors, whereas we don't have to. So the scaling of our machine is way lower than and less scary than other platforms, as we don't have to have these really high numbers of physical qubits to encode logical qubits.
That's very interesting, Juliette. I think that's where you're gaining competitive edge in this field, and also being like forerunners in terms of development, I think.
Yeah, and to comment on the competitive edge, one could say like, but where is the advantage? Like, you're more hardware efficient, and so what? If we are all able to build these machines, why do you stand out? And one great advantage for us is that at the moment, and until our in order to reach the 2030th milestone, which is to have 100 logical qubits, we don't need to interconnect multiple fridges, which is still like a huge problem within the industry, like how to interconnect two quantum computers that are into cryogenics systems. So at the moment, and we know that eventually, like, this is going to be solved, and everyone is going to benefit from such technology. But at the moment, this is really where we stand out.
So this largely improves its robustness, the architectural part of it. It's more simpler, and it improves the accuracy part of it also, right?
The path to scaling is more straightforward.
Thanks. So before we go to the next set of questions, I would like to mention that if anybody is interested in getting a complimentary copy of the problem solving using annealing report, they can click the link which is available in the chat, and one can have access to it. So I just want to pass on this message, and probably I'll pass it on to the next session to Kalyani to take over.
Yes, thank you, Kasturi. Hello, everyone. So I really wanted to focus on technical differentiation of Alice and Bob. So before we dive into the specifics of it, I want to briefly touch on how we at Everest Group are thinking about FTQC. At its core, the challenge is simple but profound. So quantum systems are incredibly powerful. There is no doubt in that, but they are delicate, they are fragile because of the qubit states. So per our analysis, there is no one right solution to achieve fault tolerance. Quantum error suppression, mitigation, and correction need to work together to reach the stage of fault tolerance that we are all hoping to get very soon. Nonetheless, the error correction part of it has proven to be vital for achieving fault tolerance. In many advanced quantum architectures, error correction techniques are designed to complement each other, balancing scalability, noise resilience, and resource efficiency through system-level co-design, which has to be, which is observed to be one of the optimal error correction techniques so far. So we have compared different QAC techniques based on error reduction effectiveness, qubit overhead, noise resilience, scalability, implementation complexity, and so on. So few of these notable leading approaches are surface codes, like Kasturi mentioned, LPDC codes, bosonic encoding like CAT and GKP qubits, so which distribute the logical information across multiple physical qubits to detect and correct faults in real time. So Alice and Bob's architecture is very much focused on bosonic CAT qubits. So what are the technical measurement vectors you have taken into consideration to sort of proceed with this approach compared to commonly observed codes that are surface codes? Is scalability the prime factor, and what other parameters have contributed to your decision to move ahead with this technology, and what are your plans with it?
Yeah, so in
Over
terms
to you, Juliette.
So in terms of error correction schemes, so as I was mentioning, we have a noise bias by design, so like directly in our hardware, but we also still need to correct for some errors, mostly the bit flips. And to do that, there's a series of solutions available to us, and the one that are the less resource efficient but still resource intensive but still efficient are the repetition code, but also the implementation of an LDPC code that is the classic version of it, meaning that it is not gonna correct the two types of error and then being a very resource intensive, but rather only focusing on the bit flip, so that we can still have this advantage in resources, in physical resources. And at the moment, we've done like most of the theory work in order to implement these schemes, and the feasibility studies, we know how to do it. We're still building the hardware in order to fully implement them at scale. And one key aspect that the entire community is facing is the ability to have a universal set of gates. And there are some gates that are more resource intensive than others. And in order to do a certain type of gate, you have to come up with a smart way of implementing them. And we believe we do have such techniques and the ability to implement them with limited resources. And others are also like pushing in like some preferred direction based on their hardware constraints. So I would say it's at the moment, the challenge is really to make sure that we still have this advantage of resource efficiency, but without exploding our research budget by making sure that we stay fault tolerant. And this is what we've been proving so far.
So the build and scalability of FTQC systems, as you mentioned, is dependent on hardware, software, co-design, if I'm not wrong, right? So it's right to say that it's not enough to choose the right error correction scheme. The impact heavily depends on how tightly the logical stack is integrated with the physical layer. If we talk about the components of the fault-tolerant quantum systems. So how do you handle the hardware software co-design? As you mentioned, you already have the theoretical work with you, but there are certain hurdles that need to be addressed to achieve that level. So how do you plan to get address these challenges to achieve that fault tolerant level?
Yeah, so there are different type of software. There's the software that you have in order to make sure your quantum computer can run jobs, and then there's the user-facing software that is used to actually like send jobs to the quantum computer. At Alice and Bob, we are not full stack. We don't take care of everything. We really focus on our strength, which is the chip design and the ability to come up with very clever architecture. So we really work on the software that is at the interface of our hardware and the error correction schemes rather than the user-facing part. And for that, I would say the success really lies in how you team work together, because in the end you have to have like theorists, experimentalists, physicists, non-physicists working toward the same goal, and it's very hard when we don't speak the same language, like scientifically. So there's been a lot of work within Alice and Bob, and I'm sure in other companies to enable this, like this really virtuous circle of feedback and iteration on like what the theory can allow, what the experiment can do, and how to find common grounds and work together. And in terms of having this co-design, I think it's really key that like, and every player has this in mind, that it's going to be hardware specific. Like there's no solution that's one size fits all. Like we do have some error correction codes that can be like shared among multiple players, but the detailed implementation of how it happens is really close to the hardware itself, and evolves as the hardware itself evolves. So I would say attention to like the details is really key to have this virtuous circle that needs to happen. Now, when it comes to the user interface and how does a user work with their actual devices, this is not something that we develop at Alice and Bob, and we plug in with existing solutions, so front ends like Qiskit and others. And here we just want to make sure that the user has a smooth experience in the ability to use the entire set of features that's available in the front end. And for that, like I think players, like different players have done a fantastic work at building these communities, and we want to continue to nurture them and enable them to use our hardware.
Yes, I totally agree. The ecosystem is evolving at a rapid pace, and of course, everyone is moving towards being a full stack developer. That is one of the key analysis in our value chain analysis in our report as well. So as the quantum industry is moving into an early development or prototype phase, we are seeing various performance measurement metrics. It is no longer limited to just gate fidelity. It is moving towards accuracy, reliability, and of course the scalability of the system. In our report, we have used different metrics to compare different technologies, hardware, software, logical control layers. So few of them include the coherence time, noise resilience, error rates, tunability range. Then I mentioned earlier implementation complexity, pulse imperfections, and so on. So could you share some of such performance metrics or milestones that Alison Bob has taken into consideration to derive a strategic step for the next plan of action to, build a next phase of their FTQC roadmap?
Yeah, so definitely we are at a stage where, as we are all building this machine, there's no like set benchmark that allow like clearly to compare a quantum computer to another, especially if they don't have the same modalities. Looking forward, we'd all like to like be able to compare the performance at the application level and not having like to think about like what's beyond this. But we're not there yet. So as you were mentioning, we're all looking at the very core metrics of each other's platform. And for the CAD qubit, one that is very important is the logical error rate. And others could look also into the physical error rate. But for us, depending on which one you're looking at, we are able to tolerate a very higher number compared to, for example, transmons. So we found that the logical error rate kind of smooths these out if you want to compare like different modalities. But again, it's not the only thing you have to have in mind. If you want to run an application at scale, the clock speed of your entire machine is also very crucial because it's going to make a difference between a machine that runs a job in an hour compared to like days. And there are some platforms that are inherently like slower than others because of their qubit carrier. And in the end, you have to take a very complete and really dig into the details of like, okay, if I'd like to like run this benchmark application, like what would it look like in terms of accuracy of the result I could get, but also like how fast I'll able to run this job. And for the moment, yeah, it's a little bit hard to have a really one solution fits all. But logical error rate, number of logical qubit, the clock speed, and also like 2-qubit gate fidelities, for example, are good elements to look at.
Oh, that's good to hear. Thank you, Juliette.
Thank you, Juliette. Yeah, the next section that we wanted to discuss with you on is the commercialization timeline and the path to market. So in our research as well, this is one area that we really want to double click on whenever we talk about emerging technologies. We look at it as two timeline periods. One, we call it the visible future, which is 3 years out. And then we have the beyond the horizon, which is after 3 years, 7 years out. So we look at these two eras for quantum computing, and there are some clear demarcation in terms of what needs to be true for fault-tolerant quantum computing to progress from where we are today to a kind of a universal quantum computer. So in our report, we have kind of understood based on the interaction with different stakeholders that we're seeing early demonstrations of logical qubit prototypes currently, as well as some progress in error mitigation strategies for today's noisy systems, like you mentioned earlier. This phase currently, as we see the visible future, also will include the emergence of the early stage fault-tolerant architectures, those which are largely confined to labs and research institutions, and some of these stakeholders progressing very few select pilot projects. So during this period, commercial deployment is limited, and it's more about proving the fundamentals around areas like qubit stability, like you mentioned, extending the coherence time, and beginning to encode quantum error correction directly into the hardware. So these are some of the things that what needs to be true in terms of signals that we are tracking. And over the horizon is where things start to scale. And in our research, we have marked 2029 as the year in which we start to see a clear shift towards scalable FTQC systems. And by early 2030s is when we anticipate the arrival of the general purpose fault-tolerant quantum computers capable of tackling real-world problems. So that becomes more real. So in terms of commercialization, this is where we expect to move beyond early access programs with the evolution of business models as well, from cloud-based quantum services to more embedded and utility-scale platforms delivered with full enterprise integration, right? So, with this in perspective and the context of how we have conducted our research and what we believe needs to be true for, a pathway to FTQC, Alice and Bob's roadmap appears to run slightly ahead of the curve. So with the graphene, which is going to be targeted around the 2030 timeline, from your vantage point, we would like to really understand how does this timeline align with what you're seeing internally, because you're hands-on and looking at all the challenges that you highlighted in building and scaling up the system, especially around scaling logical qubits and building towards universal gate sets.
Yeah. So the roadmap that we've made available, like in winter last year, clearly states the different milestone that we need to hit in order to reach this 100 logical qubit machine in 2030. And what we aim for this machine is to really start to scratch the surface of what we call scientific value. So being able to run some jobs that are scientifically relevant and out of reach of like classical supercomputers, but will not necessarily have an impact on the global industry, and will be kind of like the tipping point of like a real advantage using quantum computers. Now, in order to reach this milestone, there's like a bunch of technological de-risking steps that needs to happen, and we need to build multiple layers of this universal fault tolerant. One of them is to prove that we have a first logical qubit, and we are actually working on that, and we'd have some announcement around this in the coming few months. The second one is making sure that we have a universal set of gates, and some of them are more expensive than others, as I was mentioning. So building on top of that, adding all of these gates, and then scaling the system. So we anticipate to have a first universal fault-tolerant quantum computer in roughly 2028, and then we need to scale that to reach a machine that will have 100 logical qubits in 2030. Now, if you look at what's happening globally in the industry, there are players that are claiming they'll be arriving there a little bit sooner, a little bit later, but we all know that roughly around 2030 minus or plus a few years will be when we will have this kind of like breakthrough as a community of like demonstrating a clear advantage. And I think the question is rather than like who's going to get first, who's going to have this ability to demonstrate this advantage now, is how are we going to grow this community around such a machine? Because in the end, even with 100 or 200 logical qubit, we are not going to be able to tackle any type of industry industrial useful like use cases, but rather anticipate for it. And we still need to work collectively to build on these like great milestones to bring these technology in production and demonstrate a clear advantage for the industry.
Yeah, I think that's a more grounded perspective, and it kind of clarifies a lot of those, what needs to be true and the signals that we should be tracking. And clearly, I think we've been receiving quite a lot of requests and attention on what quantum computing means for enterprises. Some of our enterprise customers are looking at, for example, quantum security, post-quantum cryptography in the context of, what needs to be done today to protect the data and the cover time for existing data throughout the next 5 years if we're expecting a quantum computer to break the existing encryption and decryption algorithms. So similarly, if we look at the enterprise readiness and use case inflection points, so if we are talking about the customers and potential users of these systems, what do you think are certain tipping points in terms of where we see the real value being unlocked? We have kind of segmented the use cases as cryptography, simulation, optimization, and simulation. And these are, at a very high level. So solving for certain optimization problems. Can we simulate certain scenarios? Like, can we build Earth models quite fast? Can we build for, climate models which can forecast climate change effects in different regions of the world? Can we solve for material science, discovery related issues, or even the drug discovery application? So all of these are, kind of curious to know what needs to be done in terms of understanding where the real value is. So from your perspective, what should enterprises do, and how should the preparedness be approached? And are there any perspectives that you would like to add there?
Yeah, no, definitely. Thank you for this. In terms of what enterprises should look at, I would say the first step is really to identify within your business, like where could quantum accelerate or unlock some potential application that classical methods can't today. And this is really up to your own activity. There are, like, as you mentioned, like classes or problems that exist that quantum computers can tackle, but they are not going to be able to solve everything. Now, the good thing to do after having done this first identification is to prioritize them in terms of like which application will be impacted first by the arrival of a fault-tolerant quantum computer. And for this, there are a lot of studies out there around quantum resource estimates. So understanding how many physical qubits, how many logical qubits, at which error rate, and so on, you'd need in order to implement such algorithm. And if you look into the detail of these, you'll start to see that some numbers are very, very high and unlikely to happen in even the next, like the early next decade. So they might be a bit deprioritized in terms of use cases that will be impacted. And if you look at the ones that will come closer in time, and here I'm thinking about simulation of a strongly correlated system of a certain size that are amenable to quantum computers, then a machine with roughly 100 of or a couple hundred of logical qubits can then tackle such simulation. And if you look at and this is where like Alison Bob is really transparent and try to bring as much I'll say scientific honesty to the table, is that yes, there's potential, for example, for optimization type of workflows, but at the moment there's a lot of I will say incompatibility with how we know quantum computer works to implement such application. And one of them is like how to handle and load data on a quantum computer when we don't have this capacity today with our machine. Again, a good thing to do is to follow the field, try to understand who's leading what in terms of development, and see if there's a breakthrough. Because this is what we know today, but there's been great progress in resource estimate for Shor, for example, for FEMOCO, or for other type of algorithm, and it could happen. It could happen in the next 5 years or so, that we also have like breakthrough as more people are researching these type of algorithm, and we find new smart techniques. So following the field like precisely and seeing like who's leading what in terms of scientific discoveries is key to making sure you're tracking what matters.
Absolutely. Yeah. Awesome. So I think you've already highlighted some of the points that I had in mind with regards to, how does the roadmap that Alison Bob currently has, roadmap to 100 logical qubits by 2030, what kind of assumptions do we need to have, and where and when the utility will emerge? I think you've already highlighted some of it, but anything else that you want to add?
No, it's that's what I wanted to say. I think maybe something, and you hinted to it a little bit, is that the access to such quantum computer will be fairly different. We're talking about machines that have a really strong scientific power, and even if we all want to build a community around it, it's unlikely that they will be available on a public cloud, per se. So that's why it's very important for the community to start working and building this really strong relationship with the hardware vendors and different like quantum computing players today, because we all know that accessing such resources once they will become available will be a challenge compared to what it is today.
Absolutely. Yep. Awesome. So over to the next section, Kasid.
Yeah. So that's what I want to touch upon, Juliette. You mentioned a little bit on that, the ecosystem part of it. Like you have to keep watching. So when imagine we are thinking about big breakthroughs in technologies like personal computing, internet, or AI, and everything happens within an ecosystem. And that's what we find for FTQC, but we think it's going to be like complex, long term, and everybody needs to come to place, right? And what we also see is like two major forces which is actually driving the FTQC forward. One side, we are thinking of full stack players like IBM or PsyQuantum. They're building everything in-house, starting from hardware, qubit hardware to the orchestration software. On the other end, we are seeing like small firms and researchers who are more laser focused and focusing on specific layers like error correction or novel qubit designs. And we also feel like government are taking initiatives in terms of backing up these activities. For example, we have US National Quantum Initiative, EU Quantum Flagship Show, which is actually showing that it's not just a tech craze, but it is also becoming a sort of a national strategy. And we have government plans and goals towards that. They're also trying to provide more of long-term capital and more of regulatory clarity, which is actually required to de-risk early stage innovation. What we also find from an analysis is like public-private models are fast becoming a standard, and this is actually helping to build a national quantum advantage. All of this is moving towards creating new partnerships or fostering innovation and helping real world use cases across different industries like finance, energy, and healthcare. But at the end of the day, what we feel is it's not just about building the best qubit, but it's also about scaling it, integrating it, and making it work for real world applications. So, in your perspective, what do you think the role of partnership in Alice and Bob towards your FTQC journey going to be more critical? And how do you also think of the role of national governments and quantum missions in accelerating FTQC? Also, are there any evident public-private partnerships which is core part of your roadmap strategy? Some of this I know you touched upon earlier, but it will be nice to walk us through these points so that it will be helpful for us to understand how ecosystem plays a very important role, because that is a critical step that needs to be taken in achieving this FTQC realization over the long term. So, would like to hear your thoughts, Juliette.
Yeah, thank you for this. It's key, really, partnership. Like we can't really succeed as a community if there's no partnership. It's very hard to build a quantum computer, and we can't take all of the steps on our own. So we have to partner. Now there are multiple reasons to do that. Like either to accelerate because there's a piece of technology that's already available out there, or an expertise that we can leverage. And here I'm thinking about, like, for example, as we're a startup of about 150 people, raised 200 million. Like we don't have the capacity to build like a full-fledged foundry for our own chip manufacturing. So we partner, and we do have a lot of quantum vendors do partner to produce their their chips, and we rely on them. So that's a first really critical topic that we need to nail. The other ones are around making sure that the full stack is covered, and again, like relying on the community to build like open source software for having a front end, or also building on top of a common architecture for the compilation part, which is critical in order to make sure we can compile our jobs through our machine is key. Now, when it comes to public-private partnership, we've seen it through the national strategy that started roughly like about 5 years ago for major players. That it's key. It's a technology that has national interest, and as such, we've seen the event of we saw like export control rules coming out from multiple countries and so on. So we know that we are dealing in a highly somehow regulated environment, and need to work in it. And the different governments have taken like significant step in supporting their either local but also the international community. Like at Alice and Bob, we have had tremendous support from the French government through many programs, but we also have a subsidiary in the US, and we've been participating in the DARPA QBI program, which really look into making sure that there is a platform that demonstrates utility by 2033. So like we're talking about roughly the same scale as we were mentioning before, and governments are taking like significant steps in helping the community to grow. Now we always would welcome more support, but honestly, like we've been very lucky in that many governments have been there to support the ecosystem.
Very interesting, Juliette. But I'm also very curious to understand. Like we spoke about governments, we spoke about partnering with some key stakeholders. It's not going to happen alone. So what about academic institutions? Because that's where we also see very important research, the early stage research happening. Do you also provide opportunities in terms of working with them, or like how does it work for you?
Yeah, so definitely we work a lot with the academia. Mostly in Europe, but we also have like close connection with the like global ecosystem. And Alice and Bob at core was coming from a partnership between a French university and Yale. So at core we were international. And at the moment, what we benefit from is like great support from some research groups that are able to move forward some of specific topics that are of interest to them, but also to us, and being able to leverage some of these results and integrate them in our product. So it is the case mostly with, I will say, French universities. And there's also a unique system in France that allows us to, as an industry player, to have PhDs within the company. So we usually have about 10 PhD per year that are able, to focus on subjects that are key for Alice and Bob, but maybe a little bit more forward-looking than the ones that everyone on a day-to-day basis is working on.
Very interesting. So you foster open innovation in terms of taking your technology to the next level.
Yeah.
And I can see that scaling up not only from the innovation perspective, but also from the resource perspective, which is also more operational, is going to play a very important for you to gain the competitive edge in the industry.
Yeah. And like, I think it's still true that, there's not a lot and not enough people trained in quantum physics or any type of, I would say, skills or expertise that is required to work in a quantum computing company. And when we can, we support quantum workforce development, like through hackathon and other participation with the academic player, because we are very well aware that it's hard to recruit, and it's the case for everyone there. And we want to make sure that the next generation of students have are first aware of this industry, but also have the keys to succeed in it.
Great. So creating an awareness becomes an important strategy by in itself, where it can be useful for scaling up the technology to the next level, right?
Yeah.
So I have one more interesting question for you. Like, what we see is like from an application perspective, domains like quantum chemistry or material science and energy optimization are areas where classical computing is hitting a wall, and even limited FTQC performance could actually unlock breakthroughs. So this is like very much from an industry perspective. So, in terms of impact, what do you think would be the earliest applications where Alice and Bob FTQC systems will show more of economic or scientific utility? What would be your take on this?
Yeah, so at the moment, if you look precisely at the resource estimates that you need in order to do anything useful, you're closer to, I would say, something like 200 logical qubit in order to reach utility. Our bet is that by 2030, we'll bring these numbers down so that our graphene machine will be able to implement such use cases. And I'm thinking particularly at the for example, Fermi-Hubbard model, which is a type of simulation that, for example, helps you to model high temperature superconductivities that are and this type of modeling is useful in looking into simulating the properties of some materials you can use, for example, in the grid or others to have a better performance compared to existing solutions. So again, it's very, I would say, still on the theory side, even though there is some potential application of such simulation. We are looking into like really fostering the academic community in having new tools for research at first before looking into industrial use case, even though there could be some industrial breakthrough.
Very interesting. I think that is where it will help us to scale to different applications over a period of time, right?
Yeah, and at least at Alice and Bob, and we're not the only one to believe that the first application that will benefit from a couple hundreds of qubits are in like material simulation for very small like system per se compared to what a classical solution can do, but not with the same level of accuracy. And finding the limit, like the right balance of like where is this accuracy needed in the industry for such small system. This is a conversation that needs to happen between and is happening between us and industrial players to make sure that we pinpoint exactly where such solution can be beneficial for a real world application.
Okay, so that's very interesting. So in that case, the collaboration also extends to different sets of players in the industry, not just one specific application category. Whether it's drug discovery, it can be for defense, or it can be for security, or it can be for any sort of application which we can think of and in terms of where quantum can play a very important role in the next few years to come, because a lot of it deals with like potential capabilities of how the technology can be unleashed for these different applications in the future.
Yeah.
So I think
Definitely.
you are like Alice and Bob is well positioned in terms of understanding the needs and the challenges and then scaling it for different applications.
Yeah. Yeah, no, definitely. And at the moment, we really want to foster a relationship with, I'll say, because let me go back. So if you look into like who's interested in that, even among the industry, it's not everyone. We're talking about companies or verticals within an industry that are interested in these like highly accurate calculation, which is like even if you have a problem where you could not reach such accuracy might not be industrially relevant. And so having this intersection of industry relevance, but also early FTQC amenability is really hard. And there's a lot of unanswered question about it. And as the field is evolving, we really need to like proactively those discussions between the industry, the academia, and the different vendors.
Great, that's very interesting, Juliette. I have just one point to raise. We think that hybrid systems will be very helpful in terms of orchestrating workloads across classical HPC and then quantum processors, especially in the next decade. So, what is your role in terms of envisioning this hybrid quantum classical architecture in the fault-tolerant era? And then, do you think FTQC systems will replace current computing paradigms, or it is going to augment them? I mean, from my perspective, I think it's going to augment them. But like, what is your thought on that?
Yeah, no, I agree with that. And if you're a quantum algorithm person, you know that in order to get to a more precise answer with a quantum computer, you have to have a good starting point. We are not just like running a calculation out of no data. You need to have a good initial state. And for this, we really rely on classical solution, both like through simulation, but also through empirical results to provide us with a good starting point. And definitely agree that we are not going to replace classical computing. We're going to accelerate it and specific workflow. Again, not everything. And the way we at Allison Bob view things for running like fault-tolerant quantum computer at scale, fault-tolerant quantum algorithm, at scale in this early fault-tolerant era is that you are not going to be needing like really low latency between your quantum computer and your high performance resource. What you probably need is that if you want to do some or offload some of the decoding, pre-processing and post-processing for the error correction or either the management of your output of your quantum computer, then there might be something that's needed in terms of low latency between your high performance system and your quantum computer. But for running a workflow itself, if you want it to be hybrid, this low latency is not needed. The way we view it, though, it's that for example, if we take a complex system, you would run a general simulation of such system on using DFT or another type of preferred like computation method on your HPC resources. And for the strongly correlated parts, offload some parts of the workflow to a quantum computer. But they're going to work, these two solutions are going to work in parallel and are not going to replace each other. And quantum is really here to augment our overall computing capacity rather than replacing existing solution.
Thank you, Juliette. Very interesting points. So I pass it on to Isaac to sort of give a conclusion.
Yep. Thank you. Thank you, Kasturi, and thank you, Juliette. I think the section on ecosystems was quite kind of enlightening as well as encouraging for all of us to think of quantum computing as not something that's beyond our reach, but it's something that's more real and could be realized through certain critical steps that can help us augment our workflows and improve on our innovation process as well. So I mean, yesterday's call, Microsoft earnings call was one important event when Satya Nadella mentioned that the next big accelerator will be quantum for the cloud. So there are different opinions and perspectives to it. We worked on HPC data centers and all the things that go into the hardware and software for the next generation of HPC workloads moving to the cloud as well. So in this context, there is already a lot of buzz. But amid all of this excitement, it's clear that this moment calls for not just for ambition, but also for a thoughtful leadership to manage the expectations and educate the market as different stakeholders like Alice and Bob build these systems towards more real and scalable value. So one closing question, and to get your remarks on, trying to see if there are any big myths that FTQC is currently perceived with, but you would like to clear the air for some of our viewers today. So what would that one big myth be?
I would say that, and we've seen it like early last year with the demonstration of Google, that it's no longer like theory, it's really been demonstrated. And even though like as the community, we still need to make progress. We came from a long way, and actually proved that these implementation of such qubit modalities are possible, and we are way closer. I think overall we are way closer than we think in like building such machine. And I'm really excited about the next few years and see like what type of innovation will the community bring to the table, because I'm sure it's going to accelerate, and we're seeing signs of this already today.
Absolutely. I think that concludes some of our key findings as well, and kind of validate some of our convictions and what we have talking to many of the stakeholders like yourself, Juliette. And we really want to appreciate you for taking the time today to have this conversation. We really thank you for taking steps and actions towards making this a possibility. We're already on top of the hour, and I just would like to highlight that we have two important events that are coming up. Everest Group conducts events yearly, annual events, and these are called the Engage and the Elevate events. These are both scheduled to happen this year in Dallas, Texas. So I'll encourage you to, look up the website for details around these two events, and reach out to our teams and partners if you're interested to know more, and we'll be happy to engage with you. Awesome. So thanks so much for joining, everyone, and we look forward to connecting with you again in another LinkedIn Live. Thank you.
Thank you for having me. Thank you.
Thank you, Juliette.
Thank you, Juliette.